So in this lecture we talk about adjoint functors. So say we have a category C and we have a category D, and we have a functor F which goes from category C to D, and we have another functor G which goes from D to C. So you take an object X here and you take an object Y here. So X is in category C, Y is in category D. So you apply F to this object, you land in category D, you have this. You apply G to this object in category D, you land in category C, and you get this. So this F and G are adjoint to each other if we have one-to-one correspondence like this between these two arrows. So there is one-to-one correspondence. So let us write this more formally. So again we are copying this diagram right here. You have category C, you have category D, you have a functor going from C to D, and you have a functor going from D to C. So again you have this map F is written right here, this map is say G written right here, and adjunction means that there is one-to-one correspondence. So let F and G be functors as we have just described. We say F is left adjoint to G and G is right adjoint to F, written as like this. If we have an isomorphism, so this is arrows in category C, X to G5, and one-to-one correspondence with arrows in category D, so Fx to Y. So this is just notation for this arrow, this is the notation for this arrow. And furthermore we say this is natural in X and Y. So here natural means the naturality square, that is natural transformation. So we are going to talk about natural transformation in a bit. So this is how we write the bijection. So you have X to Gy and then corresponding Fx to Y. So to make it more clear, we denote the adjunction by this bar. So this bar. So again instead of writing like this, we could have started like this, Fx to Y, and then see adjunction here. So this is happening in category C, this is happening in category D. Here we are starting with category D, and then we are saying the corresponding arrow here is in category C. So we want to keep a track of this. Rather than saying F and G, we should say F and F bar, because by definition there is one-to-one correspondence. So you denote adjunction as a bar on something. So this is the adjunction operation, and it is also called the transpose. So say if you're working in category C, so you take this F here. If you want to define the corresponding adjunction, you put a F bar there. So rather than writing G, you write F bar. Similarly, you start with say something in category D, so G, you corresponding one-to-one correspondence, you should write G bar. So this is advantageous because now you have F bar here, then you can go back, you get F, and you have G bar, you do adjunction again, you get G, and that's why we also call it transpose, because you transpose again, you get the original thing. So this is important to keep in mind. So now let us come to this natural transformation or naturality. So let us now describe this naturality in X. So recall that naturality means natural transformation, and natural transformation has to be described between two functors. So it's naturality in X, so we are going to keep the other object the same. So the two functors between which we have natural transformation is this, and the other functor is this. So we have described these functors in our category theory lectures before. So we are going to change the morphism between X. So let us look at this statement more closely. So you have this function or an arrow from X to Gy in category C, and we are saying it gets mapped to F bar, its adjunction in the other category. So we are going to rewrite this statement like this. This C goes on the top and this D goes on the bottom. So we have done nothing. So this is the proper way to write a transpose. So now say there is an arrow coming in x. So there is an arrow coming in x prime going to x. So this portion f we're copying as such, and this thing we are copying as such right here. So if you have something like this in category C, to go to category D you have no option but to apply this functor f to it, because you have to land in this this arrow has to go in fx. So you just apply this functor fh. So this is kind of natural. We just copied this here and then we are putting an arrow going into x, and then just to see what is the corresponding adjunction we have no option but to apply this functor f, because there is a functor f sitting here. And this is precisely what gives us naturality. Now this thing we express in a diagram like this. So this arrow from x to gy, this sits right here, and then you apply the bar operation. You go to the arrow fx to y in category D, you go f bar here, but this f bar you pre-compose with fh. You go from fx prime to y. So this is the arrow if you compose these two, and that is where we land up here. Similarly, if you have f here, you pre-compose with h, you get an arrow. You compose these two, you get an arrow from here to here, which is x prime gy, and that's what it is. So this is the naturality square, which just comes naturally from this. There's nothing great about it. So again, it's naturality in x because we just took the c and d and put an arrow coming into x. Similarly, you have naturality in y. So now we have to have an arrow, but the arrow has to go out of y, and that you can see. You start with now this diagram dually. So this y is here, so you can only draw an arrow going out of it. So again, this portion here we are carrying here g. Corresponding transpose in category C is g prime. That is what we have written here. And now you post compose y prime here and then see what happens. So this is copied here, this thing is copied here. Now again, you are in category D. To go to have here corresponding arrow, you have to apply the functor g, because you already have gy here, so you have to have gy prime, and this information is again encoded here. So you can see first you are in g here, this becomes g prime right here, and then this g prime you have to post compose with gk to get an arrow from x to gy prime, x to gy prime. So this is it. Similarly here, this g you post compose with k, you get an arrow from fx to y prime. You get fx to y prime, just the composition. Again, this is naturality in y, and now you can see that this x remains the same, and here f(x) remains the same. So you're going from this functor to this functor. Again, this is naturality in y because you're changing the arrow y. You're keeping this x as fixed. Here, this is naturality in x because you have this y kind of fixed. So just this natural definition of one-to-one correspondence and writing this like this just leads to this. So here arrow is coming in and here arrow is going out, and that is it. So this is just reformulating what we already know from the definition. We now properly describe this naturality as a natural transformation. So again, this is how adjunction looks like. You're going from category C to category D. You have a functor going f like this and g is going like this. And say you have this object y sitting in D. So the first question which naturally arises is that say you apply functor g, you go back to C. Then you apply functor f, then you come back to D. So you first apply g and then you apply f. You're landing back in D. But on D there is also lives an identity functor which takes d to D. So what is the relationship between this functor after composition and identity functor? So is there a natural transformation connecting these two? And the answer is yes. So obviously objects here are in terms of y, so we will write natural transformation like this. And we want to now show this relationship. So we start with what we have already discussed, that is naturality in x. So we are talking about naturality in x, and this somehow leads to naturality, this naturality in category D. So again, this is the naturality in x diagram which we just described on the previous slide. So Again, this is a natural transformation. So in the previous slide we loosely said these functors, but now here we being more precise. So in the previous slide I just wrote like this, but you have this functor f here and g here. So the natural transformation is between these two functors. So the first thing which we always do for any morphism in mathematics is see what happens to the identity. So obviously if you're studying group homomorphism, you need to know where the identity lands. You're studying ring homomorphism, then you need to see that identity is properly behaving. So the first thing always is to see where would the identity be. So now we saw in the previous slide, this is the naturality, so we want to see where the identity would be. So identity would be from this, instead of dash you should have gy, because that's the arrow. So this is the identity map here. So if you, instead of dash you put gy, so this dash we also have to put gy. So you have this map. So this should be the adjunction. So that is how we write it. So this is the identity map. So now you're going fgy to y. So this is the natural transformation. Now you immediately see that, okay, we have a natural transformation like this acting on object y. So this is epsilon here. So if you put y here, then you act on this y. So that is what gives rise to the natural transformation. So natural transformation is closely related to the identity. So obviously it is going to the identity here, but it is also coming from the identity. So this gy to gy, some gy to gy will lead to a natural transformation here. So this is a natural transformation. But we still have to prove this in terms of a naturality square. So again, so this is our standard, x to gy f, then you have corresponding, if this is the corresponding adjunction, we always write it as f bar. So once you have this, now we have to connect our standard adjunction and transpose operation with this. So obvious way to connect it is that now you have to put this ahead of it. So you put this ahead of it. So now how do we go from here to here? So this portion we are just copying right here, as you can see. This you copy here. So you have fgy. So the only way now to have this x going into this is to apply a functor f to it. So you have fgy and this. So this is precisely is what is going to lead to a naturality square. So now we come to the proposition, and this proposition is just explaining what we have just said. So if you have an adjunction like this, then we have natural transformation. So this is for y and this is for x. So we are going to talk about this by using naturality in x, and dually you can use naturality in y and get this eta x. So we have to prove this naturality square. So that is, we have to show that from here we go apply this epsilon y and then k, which is the first diagram, and then we can transpose it and transpose again. So we have seen before, if you transpose it once and transpose it again, you get identity. And then from here we will transpose and then transpose again. So we went in this direction. Now we should have the commuting square, so we should go in this direction. So we should have fgy going to fgy prime. This arrow is right here and this is right here. So again this is right here. So how do we go from here to here? So obviously we can work forward or backward, and we will work in both directions. So this is kind of natural. So now you start staring at this and seeing what can we do. So first thing, obviously first arrow is just right here. Corresponding to this you have this identity map. So you're starting from here, you do adjunction, you land here. So you get this. Now you have y to y prime and you're landing in gy. So the only thing you can do is now apply the functor g here to this, you get gk. So now you just make it symmetric. gy prime, you put the id map. So id map does nothing, so this is going to collapse, and we are putting it because id map does not do anything. So we can always extend anything by an id map. So now we are here. So what we have done is only thing we have done is taken this adjunction here, and then once we had gy here, we had no option but to put gy prime here to get from here to here. We're changing the category. So this is the changing in category. So this is in D, we are in C, and then we have to land back in D. Obviously this is natural transformation in Y, so we are working in category D. So you can see Y is sitting right here. Okay, so now we have to come here. So first thing is, you notice the identity map. So we have an ID map here, we have an ID map here, but we focus on this ID map here. So instead of Y, if you write Y prime, you get this map. So we get this map. So we're just copying this thing here, replacing Y with Y prime. So nothing has been done. So you got this part. Now once you have this part, there's nothing much you can do. So this is just collapsing, so you can't do anything about it. But instead of G, now you have FG, and so instead of GY, you have to have FGY, because you have to put a functor F here, and you have to put a functor F to land in category D. Just like from here, when you were in category D, to land in category C, you have to put functor G, and you had no choice because you had already put a functor G, so you had to put a functor G here. Similarly, you have no choice. Once you have put a functor F here, from here you put a functor F here. So your transpose once, transpose again, so you have to have equality. So as we said before, and this is how the square commutes. So this is same as this by double transpose. So that is the end of story.